All right. Well, I hope everybody's having a good day. Before we get started and I talk about what this is right here, let's talk about what's going to be happening this week and next week. So tomorrow you've got something to do. Okay, the homework. Okay. Remember, if you lose a copy, you can always find an extra one on the website 24/7 or whatever additional copies I have. Okay, they're going to be over here on the door for you folks. Let's see. What's happening on Thursday? Okay, we have the first quiz over that material. Okay, anything happening Friday? Okay, well, that's not the first exam. It is the first deadline for your Algebra 2 skills last week, that little paper we did in class. I had many people come in this morning. There's still time, but by 8:05 on Friday morning, the deadline, the window's closed. So please, if you have a 79 or below and you want to take care of that, okay, come on in. Let me help you. And then next Thursday, that's your what? That's your exam. That's the big one. So everything starting yesterday through when we start the test, okay, everything's going to be fair game. And I always encourage you, it's not too early to start looking over your material. And I'm not saying take a huge amount of time every night. You know, take maybe 5 minutes. Choose one concept, one topic. Kind of review yourself on it. If you feel comfortable, great. Move on to something else or just call it a night. Okay, if you are having trouble, come on in, talk to me, and hopefully we can figure out what the gaps or the misunderstanding is. Okay, so a lot of stuff happening both this week and next. Any questions about that? No. Okay, well, this is what I refer to as a focus activity. They're pretty much bell ringers on different concepts. They may be tied directly to a lesson that we're currently working on, or it could be material that I want to go ahead and spiral back in, or it could just be something I could use very quickly to kind of introduce a new idea. Here it actually reinforces our current lesson, intersection and union. So what's important about these is that at a certain point, you're going to have a certain number of these. I'm going to ask you to turn them in. That's going to be recorded as a quiz grade. Okay, now I'm going to encourage you when you see one of these, however many times a week you get one, try to work it out by yourself. Okay, we are going to work them together, but don't wait for me to just come up here and work the problem for you, because, you know, what if something like this were to show up on a quiz or a test? You still need that ability to do it on your own. Okay, so even if you might be wrong, you know, try something. It's just like, you know, any other problem that you might come across. Okay, now I'll go ahead and tell you that this first set, you should have 4. You'll have 4 by the time we turn in the first set. Okay, so you've got focus activity number 1. The next one will say focus activity number 2. Okay, and then 3 and 4. And probably next week, because we're going into progress reports, is when I'll have you turn those in. But really, since we're working these together, all you got to do is keep up with them. Put them in a binder, someplace safe. You turn them in, 100. And it's not going to be often that happens, so please take advantage of that.
Teachers and students, pardon this interruption. Teachers, we had an ATC bus that was late, so you may have a few students walk in just a little bit behind. Again, the ATC bus was late.
Okay, so one thing, these focus activities, they are not going to be found on the website. Okay, just like any other copies, I don't have enough for everybody to grab 2. So whatever extra copies I have, I'm going to place right over here in that particular pocket for that day. So once they run out, if you happen to lose or misplace one and there's no extras, you're going to have to take the hit on the grade. Okay, I don't accept them written out. You have to keep up with the original copy. Okay, that's the one stipulation. All right, well, let's take a look at what this says. Interval of the reals. A finite interval is the set of all reals between 2 specified reals on a number line. Endpoints may or may not be included. And what were the symbols we were using yesterday for interval notation? Brackets and the parentheses, right? Okay. So the following are examples of compound inequalities. Now, we started talking about intersections, and I mentioned that a conjunction is also another term used for that. You can have a capital upside down U or V, all right, and it uses the word and. Now, when we're talking about a union, you could also describe that as a disjunction. Okay, it uses the word or, and the 2 symbols we looked at is either a capital U or V. This one's not upside down. Okay, so let's take a look at number 1. 5x minus 3 greater than 2, and or. And 5x minus 3 less than or equal to 8. So what I'm looking for is a final set of answers that are going to make both true at the same time. I want all the solutions for this inequality and this second inequality. So the first part is just solving a simple two-step inequality. Let's say I want to isolate the 5x in that first one. Well, what would I do? Add the 3. There we go. So if I add 3 to both sides, I've got 5x is greater than 5. And now how would I isolate the x? Divide through. So 5 divided by 5, x is greater than 1. Now I would encourage you, I didn't show all the steps. In fact, if I were solving the problem, this one only has 2 steps, I would probably immediately go to x greater than 1. The more you're able to do in your head, the stronger you're going to get. Now, if you need to write it out, please go ahead and do so. But I would encourage you, try to do it mentally. We'll try to grow a little bit. Now let's go ahead and take a look at the other one. 5x minus 3 less than or equal to 8. What do I do? Okay, once again, add the 3. So 5x, what? Less than or equal to 11. So ultimately, x is what? Less than or equal to 11/5. We'll just go ahead and leave that as an improper fraction. Okay. Now remember, I'm wanting to find the answers that are going to work for both the first and the second. Now I want to go ahead and write my answers in 3 different ways. I want to show it graphically, as an interval notation, and then as a solution set. Let's do graphically first, because I think that plays really well into the others. So when I say graphically, I'm thinking about a good old number line. Okay. Now, some of your teachers back in the day may have had you put, 0 right in the middle before you go ahead and put the most important values. I'm not interested in that. Here, the 2 values of interest are going to be 1 and 11/5, as long as they're in order. So let's say here's 1, here's 11/5. Okay. Now, I'm not going to go ahead and shade the final answer on my line graph just yet. I'm going to go ahead and look at these individually. This is something I got in the habit of doing. Let's say I want to show x is greater than 1. Well, what type of circle would I put on that 1? Open. Why? Yeah, it doesn't include 1. It doesn't have equality. So I'm going to put an open circle. And being greater than 1, well, I would shade above. So I'm just going to draw an arrow indicating that. See, I haven't marked on my actual line yet. Now, x less than or equal to 11/5. Well, what kind of circle? Okay, this would be closed because the 11/5 is included. And I want everything less than that, so I would shade below. So here are the 2 separately. Now, what is the intersection telling me to do? Do I want to merge the 2, or am I looking for only what they share? Only what they share. And see, this is why I like to start with the graphical representation, because what they share is the overlap. I can see that the same values are going to run from 1 to the 11/5. So I'm going to put the open circle here, close that one. Okay, in that region right there between 1 and 11/5, that's the only place where each set has the common elements. That's the intersection. Okay. Now, the other answers that I'm going to write are going to be giving me the exact same information. Well, they're just going to look differently. Remember, for interval notation, we separate our values by a comma. Well, we have a lower boundary of 1. We have an upper boundary of 11/5. How am I going to cap it? Okay, what's that, Sandra? Parentheses and a bracket on the other. And you'll notice if you compare the 2, this is saying all values of x between these 2 numbers. And that's what the interval notation is telling you. All values between 1 and 11/5. Okay, now I want to go ahead and show it one more time as a solution set. This is where you have that little expression. It looked like the symbolic definition from yesterday. All values of x. Okay, well, what did that colon mean? Such that. And then we go ahead and write my restriction. Now, in the solution set, this is where we go ahead and actually use the less than and the greater than symbols. Now, this is what it means, compound inequality. I'm going to take these 2 expressions here, and I'm going to go ahead and combine them into one statement. I'm going to go ahead and say that 1 is less than x, which is less than or equal to 11/5. And see, just look at all 3 of your answers. They're all saying the same thing. Okay. Now, the one thing I do want to go ahead and point out is, everybody okay how I made x greater than 1, 1 less than x? Okay. Does anybody want me to elaborate on that? Did the symbol actually reverse itself? It did not. Okay. Under what conditions does the symbol actually truly reverse itself? When you multiply or divide by a negative. Okay. So nobody wants me to elaborate on that. We're okay. All right, and that's it. That's number one. Okay, I found all the values of x that'll satisfy both. Okay, and I represented that in 3 different ways. Okay. Now, if I wanted you to do that, like say on your homework or test or a quiz, I would go ahead and say specifically list it as these 3 expressions. But typically, the best answer is still going to be your interval notation. Okay. All right. Now, let's go ahead and take a look at number 2. Now, there is one typo, unfortunately, where it says 5c. Okay, of course, that's supposed to be an x. Okay, because if it's not an x, I mean, you're going to be stuck. You can't go any further. But do you notice anything about number 2? It's the exact same inequalities, but now we're doing what? Okay, we're taking the disjunction. We're taking the union. Okay, so I don't need to solve them again. I know this first one ended up being x greater than 1. I know the second inequality ended up being x less than or equal to 11/5. But now I want to take all the answers in this first set or all the answers in the second set. And again, I'm trying to use the common vocabulary, to help emphasize that. So I'm going to go ahead and start with my line graph. Okay, so I'm going to put the 1, I'm going to put the 11/5. Okay, so I got to try to figure out what to shade if I now want to take the union. So I'm going to do them individually again. I want everything greater than 1, but not including it. I want everything including 11/5 and less than. Now, if the intersection was simply what each set shares, the overlap, what's the union? All of the values. I want to take everything from one set and combine it with the other into one big set. Okay, so where am I shading on my number line? Okay, so William is saying negative to positive infinity. So he says I should shade everywhere. Would you guys agree? I'm glad you brought it up. Okay, now, are there some people out there who are thinking, well, we shade everywhere except for the 1? How many people think we should remove the 1? Okay. It is actually correct that we're going to shade everything. So let's talk about that. Why would we include the 1? Okay, what do you think, man? That's exactly right. Remember, we're taking the union. Even though the 1 isn't included in its own set, it is included in the other. So the 1 is kind of taken care of by the other set. That's absolutely right. And it's something really easy to miss. Okay. Now, for this, because it's everything, some people go ahead and write it this way. I will never do so because we're going from negative to positive infinity, right? One thing I don't like to do, and this is just a personal choice, I don't like to go ahead and compare infinity to inequality because infinity isn't a specific idea. You're less than infinity. What does that mean? Okay, you can't be less than infinity, but you're going to see some people who are going to write it like that. Completely fine. I'm not going to say they're wrong or correct. I'm just going to say that I don't agree with them. So for this one, I'm not writing a solution set, this version right here. In fact, what's the 2-word phrase that would describe everything? All reals, or all real numbers. Okay, I would probably just go ahead and say all reals. Okay. Now, if you were to go ahead and put that, I'll probably furrow my brow a little bit and go, but I'm not going to count off. I'm okay with that? All right, and how would I show all reals as interval notation? Like, what are the values I'm going to put on either side of my comma? There you go. Negative infinity, infinity, and we never include the infinities. Okay, so there we go. That's the interval notation form of just saying all reals. Okay, did anybody in here solve those and at least get to interval notation? Anybody get close? At least solve the intervals, the inequalities, I should say. Okay. Well, I believe if I remember correctly, and I have to look, I'm pretty sure that the second focus activity is very similar to this one. So now that we've had a template, we've seen an example, now you'll be able to run through that. Okay. So what are we going to do with these focus activities? It is very, very important to just hang on to those. So put them someplace super safe where you know you're not going to lose them. Okay. Cool. What do we got here? Okay. Oops. All right, so let's go ahead and wrap up this lesson that we started yesterday. We had a little bit of review and brought up some vocabulary words that hopefully you were familiar with, some that you were most likely not familiar with. In abscissa, which is another word for the x values, ordinate, which is the y values. And then we went from that into sets, intersection union. We had a variety of symbols we were looking at. And then ultimately, we finished up with Venn diagrams. Okay, we're talking about the relationship. And if I'm not mistaken, we did get through this problem, correct? Okay, so we got through that one. We're good, good, good. So the only thing left is to go ahead and talk about the hierarchy of numbers. And we somewhat brought this up yesterday, but now we're going to go into it in a lot more detail. But let's go ahead and focus on what we know, okay? And let's just go ahead and build it up. The first group we have is the natural numbers. Well, what group is that made of? Or what elements make up that set? Oh, now, does naturals include 0? Doesn't include 0, but it does have your positive counting numbers. They were the first numbers you were ever taught way back in your early school years. Now, as I start to move up, the group of naturals belongs to the whole numbers. Remember, we called that a subset, a group within a group. But what's the only difference between the wholes and the naturals? The wholes have 0, so the positive counting numbers and 0. In fact, you'll notice I've got those defined right here. Here's the naturals, here's the whole numbers. Now, the whole numbers, in turn, are a subset of the integers. So they not only contain what the wholes contain, the positive counting numbers and 0, but they also contain their, starts with the O, opposites. They contain their negatives. That's absolutely right. Now, one thing I want to make sure you're able to notice, look at the naturals, the whole numbers, and the integers. What kind of values are you not seeing? There's no decimals, no fractional values. Okay? If it's a decimal or a fraction, it's definitely not going to belong to one of those three groups. Okay? Now, I do want to go ahead and point out one thing before we continue. You notice here, while those are the natural numbers, I can also use the integers to describe that. Because you'll notice, what did I put here in the top right corner? A plus. So if I go ahead and put the integer symbol z with plus, well, that means I'm only referring to the positive integers, which are your positive counting numbers. What if I were to go ahead and say this? What elements would you immediately think of? Only your negative integers, so -1, -2, -3, and so forth. Okay, so you can actually, in a few cases, go ahead and use other letters to go ahead and help figure out which one we're talking about. Now, rationals. Now, if you look down here, I'm not going to go ahead and read all this, word for word, but some things I do want to highlight. The rationals Q, here's the symbolic definition for it. So it's all expressions in the form A over B. So what am I describing here? They can be written as a fraction. That's absolutely right. So all fractional values A over B such that A belongs to the integers. What's that symbol mean? And B belongs to the integers, and B can't equal 0. So base definition, if it can be written as a fraction, it's going to be a rational number. Okay. The one thing we can't divide by is 0. All right. Now, I am going to go ahead and change one thing, because I didn't talk to you yesterday about complex or imaginary. So yesterday, when we said irrationals, we used I. Well, now that we know about the existence of these other groups, I can't go ahead and call it I anymore, because I tells me we're dealing with a pure imaginary number. All right, so you'll notice I've got a couple of options here for you to go ahead and use irrational. Think about it. The reals are broken up into what two subgroups? the rational and the irrationals, right? So if I take the real numbers and I subtract the rationals, well, what's left? Irrational. So that's why you could use r minus q. You can also write it as r backslash q. Personally, I like to go ahead and use r minus q, but that's just my personal preference. Okay, any questions on those? Now, there is one thing that we didn't talk about yesterday. If a number is said to be irrational, it has to satisfy two conditions. Can anybody tell me what one of those two conditions must be? Or let's actually think of an example. What's the most famous irrational number that you know? Pi. Okay, so let's think about pi. Okay, what is pi? 3.141592653589793238462, and it keeps going, right? Great at parties. Hello. William. Okay, there you go, sir. All right, but think about that decimal pi. What's that, Alex? You're great at parties? Oh, yeah. Well, I was saying that's, it's a great icebreaker because that immediately makes people want to talk to you if you just sit there and keep saying numbers. It's awesome. Okay, so think about that number pi. I mean, like, what characteristics does it have? An infinite number of decimal places. Okay, that's one. So it has to have a non-terminating number of decimal places. So I'll just go ahead and say decimals. So it basically has to go forever. That's one requirement. What's another one? There cannot be a what? When you're looking at the numbers. There cannot be a pattern. No pattern. Because it's very possible for a decimal value to still be labeled as rational. Okay? Because think about like some of these examples down here. What does that little bar above the 0.3 mean? That means that particular value is just going to repeat over and over again. So this would just be 0.3333333 ... Now see, it is true, this number does have an infinite number of decimal places. It is non-terminating. It satisfies the first condition. But there is a pattern. In order for a number to be irrational, it has to satisfy both. Okay? So it could be the same number or same group of numbers over and over again. Like this guy right here, where it has the 2178 below the bar. So that would be 0.2178, 2178. If there's a pattern, you're going to pick up on that pretty quick. Okay, so that's how we go ahead and tell if it's irrational. All right. Any questions on that? Good, good, good. Okay. Well, let's go ahead and extend our knowledge here. Now, the reals are one of two subgroups or subsets that belong to what we call complex numbers. Okay, now complex numbers are always going to be in this form, a plus bi. In fact, here's the definition down here, okay, the symbolic definition. It says all expressions of the form a plus bi such that a and b belong to what? R. So a and b are both real numbers, and I is the square root of -1. That's the definition, how we go ahead and work with imaginary numbers. Now, this is just kind of, FYI over to the side. How many people are completely confident if I were to give you an imaginary number or a radical with a negative, you could simplify it? So not everybody's raising their hands. Okay, so let me give you a few just for practice. If I were to give you like the square root of -36. Now, forget about the negative. What's the square root of 36? Why? There you go. You're looking for the one factor that you multiply against itself, right? 6 times 6. Makes sense. But we have a problem here. We need -36. So the only way for that to happen is 6 times -6. But simply making one of those negative, they are two completely different numbers. Okay, so what we want to do, we kind of found a way to get around this. We actually don't take the square root of a negative number. It's not possible. So I'm going to rewrite this as 36 times -1. I'm going to separate the negative from everything else. So what's the square root of 36? That would be 6. Okay, so we took care of that one. And we're going to use this definition here. The square root of -1, we just go ahead and call it I. Remember, that's how we simplify those expressions. So what's the square root of -100? 10i. The square root of -1 is still there. We just don't immediately see it because of the variable definition. All right, well, what if I were to give you this? The square root of -7. Sometimes you'll be given a radical that's not a perfect square. So it may be something like we saw earlier in the week. Okay. I want to say Connor, correct? Yeah, see, I'm getting these names down. He says I square root of 7. Because 7 is prime. We can't simplify him any further. He's not a perfect square, so he has to stay as is. The only thing I can actually simplify is rewrite the square root of -1 as I. Okay. What about this one? Square root -20. Okay. Can you help me out with that one? Perfect. She immediately says 2i square roots of 5. And think about it. How am I going to rewrite that -20? Well, I would say 4 times 5 times -1. Okay? Because 4 is the largest perfect square that'll go in there. So the square root of 4 is 2. What's the square root of -1? There's your I. And see, the 5 being prime has to stay inside. Okay? How many people remember that? Okay. So now does that make it a little easier? Okay. With so many people raising their hands, I guess the ayes have it. I would definitely say if you understand imaginary numbers, you're a great pupil. Pupil, get it? I'll admit that joke was a little cornea. I'll stop. Okay. I'll stop. Oh, we haven't even begun. Oh, just get ready. Yeah. I give a whole new meaning to the term dad jokes. All right, so complex numbers are going to be of that form. Now, there is a distinction here because some people will just, if it has I, they're always going to refer to it as imaginary. And technically, that's not correct. If it's complex, it has to have both a real and an imaginary portion. Okay, so complex would be something like, let's say, oh, I don't know, 7 minus 2i. See, we have a real value a, and the coefficient b is a real number as well. But we have real and imaginary. So a combination of two, that's what we call complex. If we're going to go ahead and call something imaginary, well, really we're referring to it as a pure imaginary number. That means there's no value of a, you only have the bi term. And in fact, I've got several examples right here. So I, 2i, pi I. So you see 1, 2, pi, well, they're all real numbers. That represents b. But you'll notice there's no term adding or subtracting that. Okay? So there is a distinction between the two. In fact, let me go ahead and kind of group this in with the reals. Okay? Let's say, how about a number 5? 5 is definitely real, right? Okay. Is 5 complex? Okay. Well, we see that the reals are a subset of the complex numbers. So let's say, how do I know that 5 is rational? By definition, can it be written as a fraction? So I can put 5 over what? I can put 5 over 1. So by the same token, could I say 5 is complex by saying 5 plus 0i? See, there's your a plus bi. Are both 5 and 0 real numbers? Yeah, so by definition, that's why he is also a complex number. But if I were going to go ahead and call him imaginary, again, not quite right, because he has a real portion. So if I were to say something like, oh, negative 5i, if there's no real portion a, then it's a pure imaginary. Okay, so let's try some examples. Why don't we start with, I'm trying to remember which one I did in the previous class. I think I started with 0. Okay. And this is what the second part of your quiz Thursday is going to be. You'll also notice there are questions like this on your assignment. Okay. So I want you to name all of the groups that 0 belongs to. Okay. And some people like to go ahead and start at the very bottom and kind of work your way up. I kind of prefer to start at the top and work your way down. Okay. So is 0 a complex number? Yes. I could write it as 0 plus 0i. So it's complex, C. Now I have to make a choice. Is it real or a pure imaginary? It's real. Okay. There's no I term there, so it is real, not pure imaginary. Now, because I decided real, is it rational or irrational? How would I write 0 as a fraction, though? 0 over 1. Okay. Now, 0 over 0, could I do that? Cannot do that. I cannot divide by 0. That's the one exception. So it's rational, so I'm going to put Q. And now we just start working our way through the other subgroups, those subsets. Is 0 an integer? Yes. In fact, here there he is. I see him. Hello. Okay. So I'm going to put 0. Is he a whole number? Yes. Okay. Is he a natural? No. So these are the only groups that 0 belongs to. Okay. So I know what you're saying. Mr. West, I'd like to try that on my own. Okay. I hear you. Let's try these two. 1/2 and 10i. So two different terms. I want you to go ahead and tell me all the terms that these values belong to. And while you're doing that, let me see if I can get the roll in before my window closes on me. Everybody was here. Let's see if it'll allow it. Yay! One student unassigned. Who is that? Oh, Cadence. Okay. Cadence is down there. Okay, so everybody was here. Post. And then post. Cool. Okay. All right, so let's see here. Who haven't I talked to in a while? How about Emma? Help me out with 1/2. So what's the first group I can say 1/2 belongs to? It is complex. Okay. Real or pure imaginary? Real. Rational or irrational? Rational. And remember, by definition, rational, can it be written as a fraction? Well, it is a fraction. Okay. Is it an integer? I'm sorry? Okay, now remember, what do we notice about integers, wholes, and naturals? No what? No fractions, no decimals. So that one, I can't go any further. Complex, real, rational. So, okay. So we did good. We got all the right ones. We just accidentally put an extra one. Okay. Let's see here. Tori, help me out with 10i. Okay. It is complex. Real or pure imaginary? Now, 10i, would that represent the A or the BI term? The BI, so that means it's pure imaginary. And does the imaginary have any subgroups? Nope. So if we classify a value as pure imaginary, that's all we can do. So we stop right there. Questions. How we doing? Not bad. Okay. Now, we have quite a bit of time. We don't get out of here until 52, so a decent amount of time. Here's the homework assignment. And actually, if you go ahead and take a look at the last couple of questions here, that's where I was choosing those values from. There's your 0, there's the 1/2. Does anybody see where I got the 10i from? It was number 20. What's the square root of negative 25? 5i times 2, that's where I got the 10i. So see, sometimes you may need to simplify those. Like, for example, 19, what is negative 6/3? Negative 2. Okay, so you just want to be careful about that. All right, so I'm looking at the assignment. Are there any problems that you would like to go ahead and look at together? Okay. And also, I'm going to go ahead and say this. If you're looking at numbers 1 through 12, you see where it's defining C and D? C is all values of x such that x is an odd number less than 9. D, all x such that x is an even number less than 9. The one thing I forgot to put in there, make it positive. Make it an odd positive or an even positive number. Because if you don't stipulate that, what does that mean? It's going to go down to negative infinity, so we're not going to do that. Okay, so we're only choosing the positive values on C and D there. Okay, so any questions you folks would like to look at together? Hey. Number 14. Okay, let's take a look. So for 14, we're going to use these three sets, x, y, and z. So I want to take y with the union of z and x's intersection. So in an expression like this, I would probably go ahead and fall back on your PEMDAS, your order of operations, which would tell you to do what? Okay, so forget about the y. We only want to go ahead and look at z intersecting x first. So let's see, what elements are in z that are also in x? There are none. Okay, so there's no intersection there. Remember, what do we call that? We say the empty set, the null set, but now we want to take the empty set and we want to go ahead and take the union of it with y. So let's say we have this set here, BCEF, BCEF, and I want to take the union of it with a set that has nothing in it. What would that be? It would just be y. If you take a set and you combine it with nothing, well, you're still going to have that original set. So 14, that's what you're looking for. Does that make sense, man? Okay. All right. Next. Hey. If it was a conjunction, oh, if this one were an intersection, then your final answer would be this, yeah. Because there's nothing common to all of them like that. Yeah. Good, good, good. Okay, what else? Hey, I know. 15. Okay. Oh, this is a good one. Consider the set of D, all the numbers in the interval from negative infinity to 5. What's the complement of D? Okay, so first off, what does complement mean? Okay, so everything in the universe, but not in that set itself. So what do you think the universe is here? Yeah, it's negative to positive infinity, right? So it's all reals. So think about it. We already have this. We have everything not including 5 and below. But I want to go ahead and find what it takes to get all reals. Well, what's the complement? What's missing? Caution. There you go. What's missing is going to be everything 5 and above. Now, what would I put on the 5? Bracket. Because one of the things we're going to start to see when we get into rational equations, especially when it comes to domain and range, let's say I have this set right here, negative infinity to 5 not included, and I want to take the union of that with 5 included all the way to infinity. Okay. Certain intervals can be condensed. You'll notice this one ends at 5, this one begins at 5, but I can condense it to negative to positive infinity. Why? Because I'm looking at this one right here, and that one says I don't want to include 5. But the other one does include 5. So it's like I can just hook them together. Okay, I can bridge that gap. So it's because of this, that's why everything 5 included and above is the complement. Because it makes all your reals. And does that help? I'll tell you what, I will do one more. Yes. 12. It's 12. Okay. 12. That's actually been a very popular problem today. All right, so it says of 75 people with cell phones, 42 take pictures with their cell phone, and 36 use their cell phone to take pictures and send text messages. How many use their phones to send text messages? Okay. So what I'm going to do, now this is just me personally, I created a Venn diagram to organize through the information. Okay. How many people belong to this universe? 75. So somewhere outside, I'm going to go ahead and put U equals 75. And we've only got two types of people in the universe. Either you're going to use your cell phone to take pictures, or you're going to go ahead and use it to text. Or it could be both, right? So I'm going to draw two overlapping circles. Let's say this is the number of people who take pictures. This is the folks who text. Okay. Now, what do we know about these people so far? What information was I given? There you go. It tells me that 36 use it to take pictures and send text messages. Remember, and is what? That's an intersection. So right here in the intersection, the overlap, I'm going to put 36. Now see, we're going to build on that. How does that help me? What else do I know? There you go. Connor is now saying, okay, well, we know 42 people take pictures, but it doesn't say 42 people only take pictures. Is it possible that if you take a picture with your phone, you could also text on it? Okay. All I know is that this circle right here, the one that represents the pictures, whatever number I put here, both of these have to add to the 42. Because even though those 36 people, they're texting, they're also taking pictures. So what's going to go in that little crescent region? 6. So see, 6 plus 36 is 42, but I know out of that, 6 people only use their phone for pictures. Those 6 people are not texting on their phone. Does that make sense? Okay. And see, now we're going to go ahead and build again. How can I find the number of people who only use their phone to text? Now we want to subtract. Are there any people in this universe who neither take a picture or text? No. So there's not going to be anybody outside these circles, right? So I know that this plus whatever I put there should total 75. Okay, so somebody help me out. What is 75 minus 42? 33. Now also this one could possibly go both ways. I'll go ahead and tell you what I believe the answer is. It says, how many use their phones to send text messages? I would go ahead and say 69. Where did I get that number from? There you go. Now, some people were saying that it's only 33, but for me, it's the way the question is asked. It says, how many people use their phone to send text messages? It didn't say anything about them taking or not taking pictures. Okay? As long as they're texting, that kind of says to me I would include those overlap folks. Now, if it said something, how many people only use their phone to text, then I would put 33. Okay? So I would be very careful about, the question itself. Okay. How we doing? Good? Okay. All right. Well, that's what we're going to do when we come in tomorrow. Any additional questions, we'll go ahead and take a look at. We'll get this turned in, and we will start graphs of functions, which you'll have your next set of notes up here tomorrow. Guys, thank you so much. You did a great job again.